In this video, we shall review how to calculate the voltages at different nodes in a circuit. The circuits we shall be looking at are those with a voltage source at one end and another voltage source at the other end. We'll start by reviewing positive and negative voltages. A positive voltage is one in which the negative side of the supply is connected directly to ground. A negative voltage is one in which the positive side of the supply is directly connected to ground. So this is positive 24 volts and this is negative 20 volts. We do not indicate the negative sign because the symbol already shows that the positive side is connected directly to ground. The analogy we'll be using to solve these problems is the vertical number line. If this line represents a ground, anything below that represents a negative voltage, and anything above that represents a positive voltage. Positive 40 is greater than positive 20, which in turn is greater than 0, which is greater than negative 20, and negative 20 is greater than negative 40 volts. We need to be able to estimate the voltages at any point on these number lines. So if we start with line A, this point, which is referred to as a node, we can estimate is close to 70, so we'll say that's about 60 volts. If we go to line B, well, this point is between minus 20 and minus 80 volts. It's kind of closer to minus 80, so we can estimate about minus 70. If we go to line C, our points are minus 10 volts on one side and 45 volts on the other. 45 volts is greater than minus 10. This point here we can see is less than 0, so we can say about minus 5. Finally, for line D, 20 is greater than minus 60 volts. This point is above 0, so we can estimate that to be about 10 volts. For actual circuits, the voltages at the various nodes M, N, P, and Q are very much going to be dependent not only upon the supply voltages at either end, but also upon the value of the resistors. The same supply voltages may produce different voltages at N and P if R10, 11, or 12 is different. But we just need to, at this point, be able to get an estimate because this helps us with our final calculations. So if we look at line A, M is directly connected to the supply voltage, so we know that the voltage at point M is 70 volts. N is in between 70 and 25 volts. So Vn is less than 70 but greater than 25. So we'd probably guess, if we want to guess, maybe 60 volts, maybe 50, maybe 40. It's hard to estimate, but we know that it's less than 70 volts. Now, the node N and node P, because we're thinking of this as our number line, Vn will be greater than Vp regardless of the values of the resistor. When we come to Vp, it'll also be less than 70 volts, but greater than 25 volts. Probably 20 volts, maybe 15, maybe 5. It's again difficult to say, but we know that it will be greater than 25 volts. If we look at line B, we see that Vn resides between minus 20 and minus 80. So it could be minus 40. And if we assume this is minus 40, then this would be minus 60. If this is minus 50, this could be minus 60 or minus 70. Again, we have to think of values that are between minus 20 and minus 80. Vn cannot be minus 10 or 0 or 10 volts positive. If we look at line C, Vn is going to be between 45 and minus 10. It'll be less than 45 but greater than minus 10. This is only an estimate depending on the value of R10, R11. Vp could be above 0 or Vp could be below 0. In other words, Vp could be there, or it could be even that much. It all depends on the value of the resistors. Similarly with line D, N is between 20 and minus 60, and it could reside anywhere in that range. For now, we'll just say that we can estimate Vn to be maybe minus 10 or minus 5, but it could just as well be a plus 10. We just need to remember that Vn would be less than 20 and Vn would be greater than Vp, and Vp will of course be greater than Vq. Let's take a look at a couple more examples. In this circuit, the negative side is connected to ground. That makes it a positive voltage. So we have this positive 20. For V2, the positive side is connected to ground. So that makes this a negative voltage. So this is negative 40. So our number line resides between 20 volts on the top side and minus 40 volts on the bottom side. In this circuit, for V1, the positive side is connected to ground, so that makes this a negative 30 volts. And for V2, the positive side is also connected to ground, so this makes this a negative 80 volts. For this circuit, the whole number line resides below ground. Hence, this diagram, similarly this diagram, having minus 30 and minus 80. For this circuit, for V1, the positive side is connected to ground. This makes this negative 50 volts. And for V2, the negative side is connected to ground. This makes this positive 40 volts. So in order for this to correspond to our number line, we're going to have to rotate this circuit. After rotation, we have the 40 volts at the top, positive, and the 50 volts negative at the bottom. If we add in the circuit with the resistors, we have Vp will therefore be less than 40 volts and Vn will be less than Vp. When we look at this circuit, we may think that Vn is greater than Vp, but because of the polarities of V1 and V2, and we've used the vertical number line analogy, we can clearly see that Vp will be greater than Vn. Now we have listed the steps we're going to use to solve these circuits with two voltage sources. First, we're going to determine if the voltage sources are positive or negative. We're going to redraw the circuit using the vertical number line analogy. We're going to do an estimation. This always helps in a final calculation. We're going to calculate the total voltage drop, then the current, before we calculate the individual voltage drops across each of the resistors. Finally, we calculate the node voltages by addition or subtraction. Let's look at our first example. Our first step is to determine the voltage sources are positive or negative voltages. If we look at V2, we see that the negative side is connected to ground, so this makes V2 a positive voltage. And if we look at V3, we see that the positive side is connected to ground. This makes V3 a negative voltage. Now we're going to redraw the circuit using the vertical number line analogy. We see that we have 20 volts at the top and negative 50 volts at the bottom. Next, we need to estimate what we expect the different node voltages to be. Well, we expect Vn to be less than 20 volts. We expect Vn to be greater than Vp, and Vp to be greater than minus 50. So it could be minus 40, minus 30. It's really hard to determine because we have not done our final calculations yet. Our total voltage supplied is going to be V2 minus V3, which is 70 volts. Having calculated the total voltage supply, we need to calculate the current. We first find the total resistance, which is 15.5 kilo ohms. We know we have one path, so this is a series circuit, so we must add the individual resistors. We use Ohm's law, 70 divided by 15.5k to give us 4.52 milliamps. Next, we calculate the voltage drops across each of the resistors. We're going to use Ohm's law. Vmn will be the current times resistor 5, which gives us 9.94 volts. Vnp will be the current times the value of resistor 6, which gives us 14.92 volts. And Vpq will be the current, 4.52 milliamps times 10k, which gives us 45.20 volts. Having calculated the voltage drops and done an estimation, we're in a better position to calculate the node voltages, because based on our estimation, Vn should be less than 20. So we're going to take 20 volts, we subtract the voltage drop across resistor 5, which is 9.94 volts, to give us a voltage at point N of 10.06 volts. We know that Vp will be less than Vn, so we're going to take Vn, subtract 14.92 volts, which gives us minus 4.86 volts. We can see minus 4.86 is less than 10.06, but minus 4.86 is also greater than 50 volts. So our values are within 20 volts on one side and minus 50 volts on the other. As a checkpoint, if we subtract the voltage drop across R7 from Vp, we have minus 4.86 minus 45.2, which gives us minus 50.05 volts, which is what we get at V3. We can use multisim to check, and we see we get, for Vn, we get 10.1 volts, for Vp, minus 4.84 volts.